Okay, so I'm gonna repeat myself because I forgot to hit record. So the like I was saying though, the important thing here is the sign convention, right, for omega and alpha, and it's basically just that if x points to the right and y points up, then rotations that are counterclockwise will be considered like positive or having uh, positive angular velocity, and ones that are clockwise. Wait, I said counterclockwise, right? I forgot what I said. I'm a little flustered. Jesus Christ. So counterclockwise is positive, clockwise is negative. Okay, that's the important thing here. Is that good? Does anybody need me to say anything more about these? Like I said, I don't think they're super important. Um, or I shouldn't say they're not important. I should just say that people are probably mostly good with these, I think. Cool. Okay, so I'll just keep an eye out for questions in chat in case anybody has anything. So next thing is torque, right? This is very important. This is the equation that we should have. I put like a little p here to indicate that it's important to specify an axis of rotation, right, before you start trying to calculate torques, because uh, depending on your choice, you could, well, in static equilibrium, it won't matter, but depending on your choice, you could get a different value here, I think. But you want to specify like an axis of rotation and a point that corresponds to that, like on your sketch of the situation, before you try to do anything with this. I think this is probably fine. Note that for an angular acceleration that is counterclockwise, that would be considered positive, right? And an angular acceleration that is clockwise would be considered negative, okay? So again, counterclockwise, positive, clockwise, negative, right? And the way that I remember this is that it's the exact opposite of what I would expect. But it does come from the math. So there's a reason it's like this. So moment of inertia, right? This is kind of important. And you won't have to do any like integral calculations of moments of inertia, but you should be prepared to calculate the moment of inertia of like a couple point masses maybe, right? And this is the formula that we use. It's just a sum. So say you have like three masses, right? And they're all different distances from the axis of rotation, right? This is what this r sub I indicates. It's the perpendicular distance of the mass from the axis of rotation. You just crank this out, and it gives you a moment of inertia. And it should be like necessarily positive, right? We can see because masses are always positive, and any number squared is going to be, well, any real number squared is going to be positive, right? And that's uh, that's that. So do we need to have a specific moment of inertia formulas memorized? Well, no. I mean, you can put them on your sheet, right? And I actually have like a table here, and I think that maybe you might want to just copy these down. But I'm going to just talk about one other thing before I scroll down so you can see that. And this thing that I want to talk about is that because the moment of inertia is defined as a sum, right? If we have multiple objects, we can just add their moments of inertia together, right? Um, but this is assuming that they're rotating about the same axis, or that we're considering their rotation about one unique axis. And so like the example that I'm just mentioning here is like if you have two rods sort of, joined together, right? So they form like a plus sign, and your axis of rotation is, say, like right in the center here, either, going into the screen or coming out of the screen, then the moment of inertia of this like combined object would just be the sums, or the sum of the two moments of inertia, right? And so for a rod about its center of mass, it's 1/12 ml squared, so we would just add those two together and we'd get this. So for a moment of inertia for point masses are the distance from the axis of rotation since they don't have a radius. Yeah, absolutely, right? Yeah, point masses by definition can't spin about like their own axis because they don't have any extension in space, right? So for a point mass, it is the distance, the perpendicular distance from the point mass to the axis of rotation. Right. Is everybody good with this idea though, that like if we have multiple objects and we're talking about the same axis of rotation, we can just add the individual moments of inertia together to get the total? Is that good? I don't know that you had any like homework problems like this, but I just want to, make sure that everybody's okay with that idea. And again, it just comes down to the fact that it's defined as a sum, right? Okay, so if people are good with that, we can move on. I will show you this table that I found. I would say you should probably have all these moments of inertia on your formula sheet, except for maybe this one in the bottom left corner. I've never really seen this one used in this class before, right? So with the exception of this one, in the bottom left-hand corner, you probably want to have all these on your formula sheet. So I don't know. I'll just give you like a minute or two to copy this down. But these are going to be good things to have. There should also be like a table in the textbook, I'd imagine, right? Can somebody confirm? I mean, it'd be a pretty shitty textbook if there wasn't a table, but yeah, okay, cool. And if there are like any moments of inertia that are in the table in the textbook that aren't here, like I wouldn't worry about them. These are the important ones. Okay, cool. Well, I'll scroll down a little bit then. So remember, torque is defined as a cross product, right? It's ooh, yeah, parallel axis theorem. I should put that in here too. The bottom right. A combination of top right and parallel axis theorem. Yeah. So you could get the moment of inertia of a rod about its end by applying the parallel axis theorem to the moment of inertia of a rod about its center, right? That's something we can do. But I mean, we don't have to do that if we just have a ready-made formula for it, right? Which is this. Let's see here. Yeah, let me put the parallel axis theorem in here really quickly. So let me say, like, if we know the moment of inertia of an object for an axis of rotation passing through its center of mass, we can determine its moment of inertia about any axis parallel to the center of mass axis with the parallel axis theorem, which is like this, right? It's like the moment of inertia equals the moment of inertia about the center of mass plus, let's say, md squared, right? So remember that these axes that we're thinking about here have to be parallel, right? That's why we call it the parallel axis theorem. And m is just the mass of the object, right? And d is going to be the perpendicular distance between the axes. So you would just so here, for instance, in this example with the, we could just talk about this as you would use it for a rod, right? So the parallel axis theorem would allow us to use this formula in the top right to get this formula in the bottom right. And you see like these red lines, these are our axes of rotation. And I think they do a pretty good job here of showing you like that this axis for the rod on the top right is parallel to this axis for the rod on the bottom right. And so D would just be, for this case, it would just be 1/2 the length of the rod, right? And so this is important. So I'll put a box around this, and you probably want to have this on your formula sheet. Okay, cool. So torque, right? We were talking about torque though. Torque is a cross product, right? It's the basically the cross product of the vector, the position vector, and the force that's causing the torque. So that's just math. If we want to talk about magnitudes of torque, we can say like that it's RF sine theta, or equivalently it's R times the perpendicular component of the force, or it's the perpendicular component of R times the force, right? But I think that in practice, these are going to be the two that you want to focus on for calculating torques, right? This is fine too, but I think we've mostly been working with like these two. So the important thing is that you just get the angle correct, right? And remember that the theta in that sign is the angle between the position vector and the force vector. And so just make sure that that's that. So what you should do, right, is just make a very careful diagram whenever you're doing a problem involving torque, right? Like try to make it as nice and clear as you possibly can. And this will hopefully allow you to like get the trig correct when you have to do this RF sine theta thing. Okay. So I said R is the position vector that takes us from the axis of rotation to the point where the force F is being applied. And this means, right, before attempting to calculate a torque, you need to first specify the axis of rotation. So just before you do anything, right, make sure you specify the axis of rotation. Because your R vector depends on that, right? So you want the sine of theta to be in the same direction. I'm not quite sure what you mean by that, but like you want to make sure that theta is the angle between your position vector and your force vector, right? So your position vector, right, like as you probably will draw it, takes you from the axis of rotation to the point of application of the force. But what I would suggest you do is after you've drawn your position vector and your force vector, redraw your position vector so that it now has its tail at the tail of the force vector. And the angle that you see like those two arrows make is the angle you want to use, right? Does that make sense? I'm like kind of tempted to try to draw what I mean, but like it would be very shitty because I'd have to do it with my mouse. Let me see here. Maybe I can draw it. I think that, okay, let me just do this. So, okay, this is going to be awful, but it's okay. So like this is like, let's just say there's like an arbitrary force being applied, and it looks like this maybe. And let me just make this look like a force. So that's an arrow, okay? Now, remember we have to specify our axis of rotation. So let's say our origin is like here, right? We'll just write an O to indicate the origin. So if my origin is here, then my R vector, as I'm likely to draw it, is going to look like this, right? So this is R and this is F. But what I'm saying is that you probably want to redraw your position vector. So now that its tail is at the same point as the tail of the force vector. So like this, right? This is what I'm saying. I'm just going to try to redraw this as best I can. So maybe it looks like that. And then I'll just put like a little arrow on it. Okay, so this is R, I've just redrawn it, right? I've just like moved it so that its tail is now where the tail of F is. And the point is that you want to use this angle here. This is your theta. Is this clear? I know that it's probably not clear when I'm just talking about it, but like, does the sketch make it a little bit clearer? Because this is something that I see people, and it's not just this like class, it's historically, you know, been something that physics students in the intro class have difficulty with. I think this is good. So, I mean, I'll just minimize it, and if I need to, you know, open it back up, I can and talk about it more. Okay, so let's talk about angular momentum, right? Because this is like one of the big topics that we've been talking about. And so I want to just like look at sort of an arbitrary object, right? And typically we think of like a pancake-like object that is moving, say, through the xy plane, right? I've drawn all the vectors, like this is its velocity vector, so it's kind of moving like down and to the right. But this is also spinning, right? It's spinning counterclockwise. And so this is an object that is translating and spinning about its center of mass axis, okay? So the total angular momentum of this object, right, is going to be given by like what I would call, and not just me, other people too, right? The sum of the orbital angular momentum and the spin angular momentum, right? So the orbital angular momentum is just something that this object has because it is translating, right? Its center of mass has some velocity. And the spin angular momentum comes from the fact that it's spinning, right, about an axis passing through its center of mass. And so these are the two types, right? And this is not like, I don't think this is generally emphasized in the textbook or in lectures for this class, right? And it's not just Hatridge. I think like lots of instructors do this, but it's important to know that there are basically two forms of angular momentum. And the total angular momentum, right, which I call J, is given by the vector sum of L and S, right? And so for this particular example, right, this object, as we said, is like kind of moving down and to the right. Its center of mass is moving in the direction of this velocity vector, and it's also spinning counterclockwise. So if we wanted to write out like the total angular momentum for this object, we could say, let's just focus on the z component because it only has a z component, and it's going to be given by negative RMV sine theta, right? Where this is kind of like torque, where that theta is the angle between the position vector and now the velocity vector, plus the moment of inertia about the object's center of mass times its angular speed, right? Or I guess I could say angular velocity because it's it will be either just, you know, positive or negative depending on what's happening. In this case, right, it would be positive because this thing is spinning counterclockwise, right, by our convention. And so, you know, like the way that we would see that this has a minus sign out in front, this orbital component here, is just by doing the right hand rule, right? We would take our right hand, we would point our fingers in the direction of R, then curl them in the direction of V, and our thumb points in the direction of the result of the cross product, right? And so that's why there's a negative sign there, because this component of the J vector points into the screen, right? And everybody should take a second, do the right hand rule, make sure that you can convince yourself that this vector, this component of the vector, points into the screen. Hang on with that L equals S question, because I'll talk some more about this. But I just want to talk about the other term here, right? This I sub cm omega is because, and this is a great question, is positive because the object is spinning counterclockwise, right? And so somebody's asking if it was spinning clockwise, would I omega also be negative? And yes, it would, right? And so the way that we see this for the I omega term is we just take our right hand and we curl our fingers in the direction of the rotation, right? In the direction of the angular velocity. And our thumb points, sorry, I shouldn't have said in the direction of the angular velocity. You just take your right hand, curl your fingers in the direction that this thing is spinning, and then your thumb points in the direction of the corresponding spin angular momentum, right? And so, let's see, somebody's saying, wouldn't it point out of the screen? Well, the spin angular momentum in this particular case does point out of the screen, yes. And that would be our positive z direction, right? So positive z comes out of the screen, negative z goes into the screen. And that's why we wrote negative RMV sine theta, but positive I CM omega here, okay, for the sum of the spin and orbital angular momenta. So let's see here. So would it be wrong to say L equals S was the question? So here's the thing. You can have orbital angular momentum sort of convert into spin angular momentum, right? Like that quiz problem with the asteroid. That was the idea there, right? Is that like, or the two asteroids, right? The small asteroid is zooming through space, and it collides with the large asteroid, like tangentially, kind of, not exactly, but almost tangentially. And so they stick together, and afterwards they start spinning, right? So in that quiz problem, there was initially just orbital angular momentum because the large asteroid was not spinning and the small asteroid was being treated as a point mass, right? So it can also not have spin angular momentum. Then after they collide and stick together, we have spin angular momentum, right? Because now they're like one combined object and they are, like by hypothesis, spinning about an axis passing through the center of mass of the large asteroid. So somebody's saying, can I go over when to use orbital momentum compared to spin momentum? Yeah, that, I mean, and so the question you should ask yourself is, I don't know, maybe I'll put this like, let's see here. Okay, let me do this. So let's just say, right, like get this out of the way because I think we're probably all good with this idea. But the idea is that in the absence of external torques, the total angular momentum of a system is conserved, okay? So let's just all agree that that's true. And we can come up with like sort of an outline of how to approach a problem like this, okay? So the blueprint for solving these kinds of problems might look like, and let's just do it step by step, okay? So you want to ask yourself first ask yourself which objects, let's just say there's more than one, right? Like, and I just sort of be thinking about the quiz problem as I go through this procedure here. So first ask yourself which objects are spinning about their own axes. These will have spin angular momentum. And then let's say next, ask yourself which objects are, or let's say it like this, which objects have centers of mass that are translating, right? We just mean, by translating, we just mean moving through space, okay? I don't mean like outer space, I just mean like, say in the XY plane, right? So ask yourself which objects have centers of mass that are translating. These will have orbital angular momentum. And I'm going to say contingent on your choice of an origin, right? Because remember, the orbital angular momentum depends on the position vector, right? And so you will, I think, usually know where to put your origin, or you can just decide, and as long as you're consistent, it's fine, right? So then, let's see here. Okay, so the next thing to do would be, or maybe like step 0, right, would be to choose your origin. I don't know what 0 is in Roman numerals, so I'm just going to put 0. Choose your origin, right? And what I mean by this is like essentially, let me say this, i.e. where x, y is 0, 0, right? Okay, so then we ask ourselves which objects are spinning about their own axes. They have spin angular momentum. Then we ask ourselves which objects have centers of mass that are translating. These will have orbital angular momentum contingent on the choice of origin, right? Which was our 0th step. Then we have to, okay, so this is like an outline for applying conservation of angular momentum, right? So we have to then just add everything up, right? We just like compute we just compute J naught equals L naught plus S naught, right? And we have to be, and I'm going to say this, I'll just put this in the document, being careful to respect our sign convention for angular velocities, right? And we talked about this. We just said basically, again, an angular velocity that is counterclockwise is positive, and an angular velocity that's clockwise is negative, right? So we just add these up, and we could like write this as a vector if we want, but usually it's okay to just focus on the z components, right? And that's what we did. I'm going to scroll up just to warn you. That's what we did here, right? We just focused on the z components. And we can do this because our r vector and our v vector lie exclusively in the xy plane, right? They have no z components. So we compute this, and then we just compute the final total angular momentum, right? Which I'll just write as J equals L plus S. Also, obviously being careful to respect our sign convention for the angular velocities. And then we just equate, right? We just equate J naught with J. Good to go. Is there anything about this procedure that's like unclear, or you need me to speak more on? But I think this is a good, like I said, blueprint for solving a problem where you feel like you should be using conservation of angular momentum. And so a potential, I'll just talk more like a potential pitfall here, right? Let's just say there's probably multiple potential pitfalls. But like one would be trying to convert or trying to equate, let's say like P with J, right? So basically, or more commonly what people will do is let's just say L, because this is the one that looks very much like momentum, right? Let's see, so for the pancake example, where would be the angle you use? The angle I would use would be, I would just do this thing where I take my r vector, right? And I reposition it, so now its tail is here at the center of mass, and then it would be the angle between the r vector and the v vector, right? That's what I would do. So you can't do this like most simply. Let me say most simply, this won't work because these quantities have different dimensions, right? And one of the things we look for is like, do you understand units and dimensions and stuff like that, right? This is a big thing. And like, look, right? So let me just say, because P goes like MV and L goes like RMV, these obviously don't have the same dimensions, right? These don't have the same dimensions, and like we just can't equate them. We just can't say, you know, P naught equals L final, right? Even though they look similar, there's that factor of length here in the orbital angular momentum that prevents us from doing this. So don't do this, right? I know it's tempting, and I definitely have done this before, like when I was, you know, first learning about this stuff. So don't do it, okay? Be very careful. Someone says, if you choose R arbitrarily, doesn't that change your L calculation? Yes, it does, absolutely, right? So you just want to be careful to pick an origin and stick with that choice, right? Much like we did with linear kinematics, right? Like when we were talking about or projectile motion, we would always, like, you know, at least implicitly decide where x equals 0 and y equals 0, right? And it was fine as long as we respected that choice that we've made and we were consistent with it, right? And it's the same thing here. So, you know, once you've decided where your origin is, or maybe you've been told where to put the origin, right? Just respect that choice and just stick with it, and you'll be totally fine, okay? So is everybody good with not trying to equate the linear momentum with the angular momentum, though? Because I don't want to see anybody doing this, right? Let's see here. Here's like a stupid one that I've definitely done before, right? And so I'm just going to talk about this too. And so I'm going to say a potential pitfall here is writing 1/2 I omega squared when you meant to write I omega, or vice versa, right? Because this is our spin angular momentum, and this is rotational kinetic energy. And they look similar, right? Because one has I, the other has I, one has omega squared, the other has omega, right? And it's kind of easy to accidentally write the wrong one, you know, in the heat of the moment. So just however you have to remind yourself to, you know, write the correct thing, like maybe on your formula sheet, like you just, you know, put it in bold or use exclamation points or whatever it is that you do to make sure that you don't make a silly mistake like this, right? Because like I'm doing my PhD in this shit, guys, and I've done this before, right? So I would think that under the wrong circumstances, none of you is immune to doing this, okay? And let's just go with that. Yeah, we can do it. We can look at example problems later. We're almost done talking about the conceptual stuff, probably another like 15-20 minutes, and then we can get into that. We can look at some examples. So don't do this, right? Don't write the rotational kinetic energy when you mean the angular momentum. Yeah, hey, what's up? And don't write the angular momentum when you mean the rotational kinetic energy, okay? Let's see what else is there. These are really the two big ones, I think. You know, like also, let's just say using the wrong angle. This we've talked about, and I would try to just write that off as a trig error and not take too many points off. Okay, so you know it's not gonna kill your grade, but obviously it's better if you don't lose any points as opposed to even like 1 or 2 for something like this, right? So I'll say using the wrong angle for sine theta. And again, the way that you avoid doing this is you make a sketch, a very careful sketch, okay? Okay, I think that's all I have for the potential pitfalls for angular momentum. If anything comes up as we move through this, I'm, of course, willing to just come back to this list and update it. But that's all I've got. I'm going to talk like super quickly about rotational kinetic energy because like this is not something that is. Let me just say like for our purposes, as I've said here, conservation of angular momentum will be more often what we want to think about than conservation of rotational kinetic energy, right? So just trust that that's the case, um, and bear that in mind, right? But if we need to, right, for instance, like calculate the total kinetic energy of the pancake object that we were just discussing, it would simply be the sum of the translational kinetic energy and the rotational kinetic energy, right? And so that looks like 1/2 mv squared. We should all be very familiar with this, plus 1/2 I omega squared, okay? And just to remind you, don't write 1/2 I omega squared when you mean I omega, and vice versa, okay? This is like all I really think I need to say about rotational kinetic energy. But if you have a question about it, we can definitely discuss. But I'm going to move on to the static equilibrium thing, right? And this is, I want to say that if you remember Newton's laws, the stuff we were doing in like week 2 and 3, and you feel good about calculating torques, then this is not bad, right? Because we just set everything equal to 0. We just, make a sketch of our situation, and we say, well, the net force in the x direction is 0, the net force in the y direction is 0, and the net torque about any axis, right, is 0. But that doesn't mean we don't have to be careful specifying our axis of rotation, right? And I want to say there's, at least for us, there's never any reason we can't just say that our axis of rotation is the z-axis. So you should all hope for a static equilibrium problem, right? Because like if you understand torque, this stuff is basically this part is just stuff that you're expected to already understand and be comfortable with, right? So and static equilibrium problems are pretty typical choices for exams like this. Is everybody good with static equilibrium? Do I need to say anything more about this? Okay, I'm going to move on then. This, I think we've probably, done to death at this point, but I don't think it's going to hurt if I just run through this derivation of the equations for simple harmonic motion one more time. And no, like you don't have to really worry about you don't really have to worry about Young's modulus, right? Like physicists, quite frankly, don't really care about that. So don't stress about that stuff. So it could appear on the final, right? Like because I think Dr. Nero will be writing the final exam, and sometimes he likes to have you use Young's modulus to like get an effective spring constant, but like don't worry about that for now. So let's see here. So if there aren't any torques, what exactly would we be solving for? We're like just because an object isn't accelerating angularly doesn't mean that there are no forces that could cause it to accelerate angularly, right? So you need to think about like what would happen with your object, if say like a certain force was stronger in magnitude or another force was removed or something like that, right? Because most of the time by making one of the forces in like the x or y direction stronger in magnitude or removing one of them, your object would actually begin to rotate, right? So the point is that you just write out an expression for the torque about a point or about an axis of rotation, and set it equals 0, right? but you might be concerned with like one of the terms in that, expression for your torque, right? Like a mass or just a force or something like that. Actually, I should say a little bit more about torque really, or static equilibrium really quickly. And so I'm going to say this thing, I'm going to talk about hinges, right? Because I sense that maybe people don't feel great about hinges. And so let me just say something like, if there is a hinge present, and I don't know, you could think of like a beam, right, that's attached to a wall with a hinge. Maybe I'll try to find a picture of what I mean here, because I think talking about this stuff is not as good as showing a picture. Let me see if I can find something here. Okay, like this. Wait. Make this bigger. Okay, I like this one, but it's small. All right, let's just do this. So, like this example, right? This is like a super typical thing to be asked to like do some calculations for, right? And a hinge it changes things a little bit, right? It makes things slightly more complicated. But it's okay because like we can very easily sort of deal with hinges. And so what I'll say is that if there's a hinge present, we can't assume that the contact force is like our typical normal force and perpendicular to the surface. So what we do is we just assert that there are x and y components to the hinge force, and we can write these as, let's just call it hx and hy. This is the best thing to do, I think, right? Is just assert that there's an x component to the hinge force and a y component to the hinge force. And if we're wrong, right, if there isn't, because it's possible, then the math will show that, right? So if we just do all the math carefully, then we'll see that maybe there isn't actually an x component or a y component when we thought there was. But there's the safest thing to do is just to assume that it has both, okay? And we can even guess about the directions they point in. And what I mean by this, right, is like obviously the x component of the hinge force is going to point in the x direction, but it could point in the negative x direction, right? So it could point in the positive x direction or the negative x direction. And the y component of the hinge force, depending on the setup of the problem, could point in the positive y direction or the negative y direction. But we can just guess. And even with the direction, right, even when we guess about the direction, the math will still show us that our guess was either correct or incorrect, right? So if you have a hinge, this is what I would do. I would just draw an arrow to the right, call it hx, draw an arrow up, call it hy, and then just note that their vector sum, whatever it works out to be, is the actual hinge force, okay? Is this good? Are people okay with this? Because as I was saying, the math will show us if we were correct or incorrect with our guess. And you won't lose points for putting a hinge force in your diagram, like an x component or a y component or whatever that points the wrong way. But if you go through and end up solving and I don't know, you do it incorrectly or whatever, you could lose points, I guess. But as far as just like the diagram goes and the problem setup, it's not something that you're kind of expected to be able to just divine, right? So that's important. I think this is an important thing to mention. So now I'm going to move on to simple harmonic motion now. Okay, I don't want to go for too long tonight, but I guess we'll just see how things are going. So this is the setup, right? And we're just going to run through a very quick derivation of what this looks like. And so we're assuming a frictionless surface, right? So there's no friction between the block and the floor. And we know, right, from like week 3 or 4 that the force exerted on the block by the spring is given by Hooke's law, okay? It's just negative kx, where remember x is the displacement from the equilibrium position of the spring. And so when we write out Newton's second law, we wind up with a second order linear, and it's actually homogeneous, differential equation. And so all we're doing here, right, in this step, in case people are still not clear on this or comfortable with this, remember that x double dot is just the second time derivative of x, right? So this is the acceleration, in other words. Now the only force acting on this thing in the x direction is the spring force. So we just rearrange this, right? We're just doing math. We add kx to both sides. It's then equal to 0. That's what makes it homogeneous. And then we want to put it in like sort of the standard form for a differential equation, which basically is to get rid of the coefficient in front of the highest order derivative, right? In this case, it's the second time derivative of x. So we divide both sides by m. Nothing happens on the right because that's 0, right? 0 divided by m is still 0. And we just do like a little substitution here for convenience, kind of, where we define this quantity omega, right? Not w, omega, as the square root of k over m, where k is the spring constant and m is the mass of the object. In this case, it's a block, right? And so this allows us to write our equation, our differential equation, like this. Now, one of the solutions, and for our purposes, the most important solution is this, right? That the x position as a function of time equals some amplitude, right? This a must have dimensions of length because cosine will not have dimensions, right? Cosine of all this junk will just give us a number. So x as a function of time equals a cosine of omega t plus phi, right? And so with this in hand, we can think back to like week 2 or whatever it was, where we were, talking about how the first derivative of position is velocity and how the second derivative of position is acceleration. And we just do the math, right? We just like sort of crank the handle on this, and we wind up with an expression for the velocity in simple harmonic motion and the acceleration in simple harmonic motion. Now, I missed some questions, but I think somebody was saying damping. Yeah, don't worry about damping. That's very mathematically complicated, right? So, you don't have to stress about that so much. Like if you take dynamical systems next year, which I think most of you will, or demonical systems as I call it, you'll talk about that, there, right? You'll go crazy with simple harmonic motion and all that. But like for the time being, no, don't worry about that, okay? So this a is the amplitude, right? Now I think like the book uses some stupid notation like x sub m or something like that, right? I don't know why it does that, it's weird. But let's just call it a, okay? I think this is the most suggestive and it's the simplest. We don't have to write any subscripts. Now phi is the phase constant. Now phi is just a math thing that allows us to basically use cosine and sine to model simple harmonic motion, whatever the initial conditions might be, right? So this is just math. And I would say that it doesn't seem like, based on what we've done so far, it's been super important, like homework assignments and stuff. So if this is a little hazy, I wouldn't stress about it too much. But the point is that we might have to use this depending on the initial conditions. Because we might have some system where we can't model it perfectly with just a cosine omega t or a sine omega t, right? We might have to, like, when we're imagining the position, say, as a function of time, we might have to shift it a little bit to the right or to the left so that it actually matches what is happening. And that's where phi comes in. That this is what allows us to do that, right? Because all this does from a math perspective is it just like shifts our function to the left or the right. Maybe I'll like plot some stuff here so we can see what this does, right? So let's just say for, I don't know, we have like an amplitude of 5 meters or something, right? And an angular frequency of let's, I don't know, let's also say 10 or something. And let's just see what this looks like, right? So this is where there's no phase constant. And we'll plot this from like t goes from like -5 to 5 or something, right? So this is, maybe we'll do like a smaller range of values like this, okay? So this would be great if, because remember on the vertical axis here we have the position as a function of time, and on the horizontal axis we have time. So this would be great if our object was at maximum amplitude at time t equals 0, right? But sometimes it's not. And so like we could just, let's put something in here. I don't even know what a reasonable number would be. Let's just say it's like 0.5 or something. Notice how that shifted my cosine function to the left, right? So now what we're saying is that for instance, this could model simple harmonic motion where the object isn't exactly at maximum amplitude at time t equals 0, right? Because we see maximum amplitude is up here, it's at 5, and at time t equals 0, it's at like 4, right? So this could be, like I said, it's just a math thing that allows us to model simple harmonic motion for sort of any kind of initial condition we might have. But again, it's not even that important, okay? It's not something you need to lose sleep over. And remember, right, that you can always just whip out your calculator and plot these things, because plotting cosine and sine is not difficult, right? I mean, you just have to make sure your calculator's in radians and not degrees. You're good to go, okay? So let's see. So max amplitude should always be at t equals 0. Well, if there's nothing in the problem statement that tells you you can't assume that, then that's fine, I think, right? So just, read carefully, right? Because if, for instance, they tell you it's like, in so many words, that at time t equals 0, the simple harmonic oscillator is not at maximum amplitude, it's at like some value, then you have to include phi, right? You have to include the phase constant. Otherwise, it's fine to just assume that it's at max amplitude at time t equals 0, right? So just, read the problem statement carefully and do the math. And remember that you can plot these things, right? Like you don't need Mathematica to plot, like a simple cosine or sine function. It's just, something that your TI 83 or whatever can do, right? And I just want to stress that it's an important thing to keep in mind. So we were saying, right, I'll table those questions about phi for the time being. Then we can come back to it later if people still feel like it's hazy or they're not comfortable with it. But just want to point out, right, that we can come up with these expressions for the velocity in simple harmonic motion as a function of time and acceleration in simple harmonic motion as a function of time by taking derivatives, right? Time derivatives. And so we get these functions, right? So these, like, they're in boxes, so I would say you should have them on your formula sheet. This is in a box as well, so have it on your formula sheet. And double check my math, because you can't trust me to do derivatives, right? But I think this is good. I think this is good. So is max acceleration at where the trig value is 0 or 1? So max acceleration should be where the trig function evaluates to -1, and we will talk about that, right? Because these things are bounded, these sine and cosine functions are bounded between -1 and 1, but maximum acceleration, right, would be simply a omega squared, right? Because cosine can assume any value between -1 and +1, and so we just choose it to be -1. And that's your max acceleration in simple harmonic motion. Now, we have like these two formulas that are pretty important, right? So the period, and I know I said angular frequency here, and I wrote just the regular frequency, but like I did, write omega in terms of the regular frequency again. And so just remember that these are things, right? So like we could solve this equation for like 1/f and then set the result equal to the period. And then we have an expression that relates the period to the angular frequency. And if I'm not mistaken, right, somebody check my algebra here, because I would feel bad about lying to like 70 of you and maybe even more who are going to watch the recording later. But this looks like it just gives me okay, so f is omega over 2 pi, therefore 1/f is 2 pi over omega, right? And so we should be able to write that t equals 2 pi over omega if we need this. But I check my algebra because like honestly, I cannot be trusted to do math, right? I think we all know this by now. So this is important. And the other thing that I kind of didn't stress, but I want to, right, is that this relation is a thing. And this allows us, right, this should absolutely be on your formula sheet if you can't, commit it to memory. This allows us to go back and forth between an angular frequency and a spring constant if that's what we need to do, right? Providing that we have two of these things, like providing, say, that we have omega and the mass, we can get a spring constant just by doing, a line or two of algebra, okay? And so don't forget about this. This is important. Okay, cool. This stuff, is just algebra, so hopefully everybody feels okay about this. So I want to talk just about cross products for a little bit because we have, right, that the orbital angular momentum is defined via a cross product, right? And so just to remind you what a cross product is, like between two arbitrary vectors, A cross B is AB sine theta, right, where theta is the angle between them. We choose the angle between 0 and 180 degrees, right, because there's obviously two ways we could go from like one vector to the other in a sort of circular sense. And so just make sure you're choosing, the one that's between 0 and 180 degrees. And this is a vector, of course, right? The cross product is otherwise known as a vector product. So it gives you a vector. And this n hat is just the unit vector that's perpendicular to both A and B, or orthogonal if you want to be a math nerd, right? But this is something that we've worked with a bit, so hopefully everybody's okay with it. Just wanted to remind you. And then a consequence of this, right, is that if your R and V vectors, and these are the ones that we care about for orbital angular momentum, right, are in the xy plane, then your angular momentum, your orbital angular momentum will point in the plus or minus z direction. And we've definitely talked about this a bit, right? We looked at the pancake object, and I want everybody to keep the pancake object firmly fixed in their brains, right? And you could make this more sort of intuitive or maybe relevant by also imagining just like a frisbee, right? Say, you're out by the Cafe of Learning and, it's a nice summer day, you're throwing a frisbee to your friend or something, right? Like as the frisbee, the pancake, okay, I'll go back to that one more time. But like as you throw the frisbee to your friend, right, it's obviously moving through space. Its center of mass is moving from you to your friend. And the frisbee will also be spinning, right? So this is like a real world example of something that's going to have orbital angular momentum and spin angular momentum. And so so the pancake object was this thing, right? And this is just a typical physics thing, right? I actually found this diagram in my textbook from like sophomore year of mechanics. Definitely not a time I remember fondly. I mean, it was a good time, but the class was awful. And so this is what, we typically kind of think of, just some arbitrary object that is essentially two-dimensional, right? It doesn't have thickness, or it has negligible thickness, kind of like a frisbee, that is translating through space, right? It's moving in the xy plane with some velocity v, and also spinning about its center of mass as it does so. And so don't worry about finding the moment of inertia of this thing, right? Because that's not, if God forbid we had to, it would be calculus, right? And we'd have to know more about this thing than just it's, shaped like a potato, right? But this is the pancake object that I've been referring to. Okay. I think I just want to talk a little bit about sine and cosine, right? I just want to remind you that they're periodic, because on the quiz, some people, for instance, found that when they did the math, they got a negative time. And look, there's nothing wrong with getting a negative time in simple harmonic motion, because as far as we're concerned, this thing is just oscillating for all of time, right? From t is negative infinity to t is positive infinity. It's just doing the same shit, right? Over and over. And so, negative time isn't necessarily something to freak out about, but look, if you get a negative time, you can always, just add 2 pi to it and to make it positive, right? And that's fine. And so are people good with this idea that these things are periodic? They just repeat themselves over an interval of 2 pi? Is that good? And again, you can always check this on your calculator if you need to, right? If you have a brain fart or something and you need to remind yourself what the period of sine and cosine are. Well, no, I mean 2 pi, right? Because we can look at, let me just make this back to, let me just do this, cosine t. And let's do it from 0 to 7, or I don't know, something like that. And so the point is that here at 0, it's at 1, right? So at t equals 0, this evaluates to 1. And then at t equals 2 pi, right about here, it evaluates to 1 again, right? And so, look, and we can make this stronger. We could even say, for instance, that sine of theta plus 2 n pi, cosine of theta plus 2 n pi, where n is an integer. Jesus, let me try this one more time. There we go. This is true, okay? And just because I'm 12 years old, I'm just going to say something that I said in recitation the other day. So, we could literally write that sine of theta plus 420 pi equals sine of theta, right? And cosine of theta plus 420 pi is cosine theta. So if you get, a negative time and you really want to, just meme, you could add 420 pi to it and still have your trig function evaluate to the same value, okay? Incidentally, we could also write, this isn't going to be important, but I just feel like I should say this, the tangent of theta plus 69 pi is tangent of theta, okay? Just trying to put this in a way that I think will make it memorable for you. So this is all mathematically true, okay? But as far as like also and I think we touched upon this too, the thing is that these things are bounded between -1 and +1, right? Both sine and cosine. And it doesn't matter what our argument is. It doesn't matter what this theta is. Like I can just show you if I wanted to write like cosine or plot cosine of 100 times t, like it's oscillating very, very quickly, right? But it's still bounded between 1 and -1, right? So keep this in mind, that it's bounded, that sine of anything is bounded between -1 and 1, and cosine of anything is bounded between -1 and 1. And one more time, you can always just plot these things to remind yourself that this is the case if you can't pull it out of your brain. Or just put it on your sheet of notes, right? I don't think that there's anything wrong with having this on your sheet of notes. Okay. That is, I think, everything that is important conceptually. Do people have like things they think I might have missed, or questions or anything before we maybe look at some examples? Is this comprehensive, or what do you guys think? The pendulum stuff, I would have those equations on my formula sheet, at least for a simple pendulum, right? So put that stuff down, but also remember that it's like the exact same thing as it is simple harmonic motion, right? That it's like that all this stuff for a pendulum is governed by basically an equation of the exact same form as what we found for the x of t thing up here, right? You just have, I mean, literally for like a pendulum, it's just going to look something like theta of t, right, is like, and let's just write big theta cosine omega t plus v, right? Like this. And so the only difference here is that we're now talking about the angular displacement from equilibrium, right? Whereas with like the above equation, we're talking about the linear displacement from the equilibrium position, right? But this is it. It just works out to be this for our solution. Okay, so essentially, understanding simple harmonic motion for the case that we just discussed, right, with like a block attached to a wall by a spring, all that conceptual understanding will serve you very well for pendula, right? And that is the proper plural form of pendulum, if I'm not mistaken. Okay, but that's good. What else? Do people have anything else as far as stuff that like I might have missed that we're concerned about? Who's got something? I'll give you a couple more seconds and then we can look at some examples. Okay, if people want to look at homework problems, then sure. Let's see, number 7. Which one was that? Piston and screw. Oh, this god-awful problem. Okay, yeah. But this is a good one though, because I think that like it just emphasizes a lot of the conceptual stuff we were just discussing. Okay, so this let's do this. Okay, I don't know. Oh Jesus, I don't know how to get out of the box without expanding the box. So let me just fix this really quickly because this is going to annoy me. Okay, so I want to just write stuff. Okay. let's get rid of that. Let me rebox this. Wait, why is it not? Why is it being dumb? Okay. Rebox that, do my little thing. Okay, cool. So this was number 7 from homework. Let's see here. I have the homework up. This must have been homework 10, right? Oh, look at me. I'm such a shitty student. Okay, so I'll just take this question really quickly. Are we only in radians for oscillations and stuff, and all the other chapters are? Yeah. So basically, whenever you're working with simple harmonic motion, this is a good thing to remember, is that you want your calculator to be in radians. Okay. But it could be tricky because for, like, say, a static equilibrium problem, maybe you're given the direction of a force in terms of degrees or something like that, right? So you just have to be mindful of this. And it's not a big deal, right? It's very easy to switch your calculator from, radians to degrees and vice versa, but, like, you want to just remember to do that as you, say, go from, like, one problem to the next, okay? That's a great question. I don't want to see anybody make that mistake, but of course, like, so for this exam, I'll be grading 2 problems. And personally, that, like, I don't give a shit about the numbers, right? So as long as you do all the physics correct, I will take off the minimum number of points that I can as per, Supreme Leader Hattridge's discretion, and it shouldn't be a huge deal, right? Okay, let's look at this one, though. This is what, like, I forget, homework 10? Why doesn't it say which homework this is? Like, why would I have to navigate away? I'm pretty sure it's 10. I don't want to, like, go back. Okay, so what we would want to do here is, I'm not going to draw it unless people really want me to, but I'm going to say, consider the free body diagram of the bolt, right? We would have a normal force pointing up, and let's call this normal force just N. And the gravitational force pointing down. And we'll, of course, just call this mg. Another thing, by the way, is that, like, a lot of you, I don't know why this is a thing, and it's not a huge deal, I guess, but, like, so many of you just write F sub g for the gravitational force. Like, why don't you just write mg, right? That's what it is. Does, like, Hattridge make you do that? Or does he tell you to do that? Because, like, I don't know, it seems kind of silly to me, but anyway. So we want to think about the net force in the y direction on this thing, right? So the net force in the y direction on this, right, because we have motion in the y direction, of course, it's moving up and down, is going to be the normal force minus mg, right? And this is going to equal may, but with some qualifications, okay? Because the acceleration is changing here, right? So if we, and this is also good, right? Because, like, the thing is, people are asking about this phase angle and all this stuff, right? This would be a situation where we don't have any information about the initial conditions, right? So we could just assume, right? I'll say in this case, because we have no information about the initial conditions, we can assume that, and I think, like, they use sine here, and I'm just going to do the same thing, but we can assume that y of t is simply given by a sine omega t. Okay, okay, it's not a huge deal, right, about the FG thing. It's just, like, it just seems kind of indirect. So in this case, because we have no information about the initial conditions, we can assume that y of t equals a sine of omega t, right? Because there's no reason this thing can't be, based on the information that we're given, at the equilibrium position, right, at y equals 0, at t equals 0, okay? This is an example of reading the problem statement and deciding how to write your equation for the position in simple harmonic motion. Now, some of you might be a little like concerned as to like the fact that I wrote sine here is instead of cosine, and remember that it doesn't matter because all of these things, like, or sine and cosine at least, are doing the exact same thing, right? They're just oscillating between -1 and 1 with the same period, right? So we can write that y of t is a sine of omega t here instead of cosine of omega t if we want to, if we feel like it, and I feel like it. Is this okay? Are people good with this? And I'm just gonna like make Mathematica take the second derivative here because I have it open and I can't do math. So just bear with me while I do this, because what we want is the acceleration, right? We want the acceleration for Newton's second law. And so let me just put this on another line. This becomes, right, filling in the details, the normal force, and I'm gonna write of t because it's a function of time, because look, the gravitational force is constant, right? This will always be magnitude mg pointing down. And then I'm gonna write m, and then what we found for the second derivative of the y equation, which is -a omega squared sine omega t. Okay, so we're getting somewhere here. And I'm just gonna write this one more time. I'm gonna clean it up a little bit by basically just getting rid of the brackets. So we could write this as -ma omega squared sine omega t. Okay, so this is our Newton's second law in the y direction. Is everybody good with the fact that the normal force here depends on time? Do I need to talk about that more? It's totally okay if I do. I just want to see if you're all okay with that idea. Okay, so is the fact that people are not saying anything an indicator that you are good with this? Okay, cool. All right, one person, that's enough. You can stop me if you're not. But so, okay, so we agree that the normal force depends on time. Now look, what I'm going to assert is that if and when the bolt loses contact, Jesus, with the piston, gee, oh wow, okay, piston, yeah, piston, it will happen when y of t equals plus or minus a. Okay, now I'm not going to really give you any evidence for this, but it just kind of seems like, right, like if we imagine this happening in real life, that the bolt will either like fly up or not remain in contact with the piston at the maximum value or minimum value of y. Okay, hopefully everybody is okay with this, and hopefully it just sort of makes sense intuitively. And so if we accept this, right, if we accept that this happens, all we need to do, because I think that when I did this for some students during office hours, it was very convoluted and not clear, and I think I can do a better job now, is that we just note, right, that like when the bolt loses contact with the piston, we have, wow, why do you keep doing that? Piston. We have that the normal force goes to 0. Okay? So we're basically in a position to solve this now, because what we do is we write something like this. We write 0 minus mg equals negative ma omega squared sine, and then I'm going to say that t is 1/4 of a period, okay? Because this is when the piston is first at its maximum amplitude. This is when the first time the piston reaches y equals positive a, okay? So we're imagining that the bolt loses contact with the piston at the very top of its motion. And so I'm gonna write that this is omega times t over 4, where big T is the period, okay? So I guess I could say, I'll leave this as is, but I guess I could write this is big T over 4 here if I wanted to. Okay, so we're going to rewrite this. We have negative mg on the left. We don't need to keep the 0 in there because it doesn't do anything. Now, we want to remember what the period is in simple harmonic motion, okay? And we had the formula up here. It was 2 pi over omega, right? So 1/4 of a period should be, let me fill this in, omega times, wow, I just forgot what I looked at. So 2 pi over omega, and then we divide that by 4. Okay, so 2 pi over 4 omega. All right, I'm getting some questions. Good. People are interacting. Let's see. Should it be cosine instead because I have... Well, the short answer is it doesn't matter, right? Because we could do either cosine or sine here. I think sine is a little easier because this sort of goes into the other question where we're saying that it's at y equals 0. Let me put this in words. Choosing sine here instead of cosine indicates that at t equals 0, y equals 0, of course, right? Because sine of 0 is 0, right? And this is part of the reason we might choose sine here, because it's in a sense easy to say that the bolt is at position y equals 0 at time t equals 0. I think it's very natural, right? It's just kind of like saying it starts at the beginning, right? But these are good questions, and I'm appreciative that people are asking. So let's just go through and keep an eye out for more questions, but I'm just going to take this to completion here. So we can get rid of negative m on both sides, right? Because we could just divide both sides by negative m. It doesn't change anything about the mathematical truth of our equation. So we then write g equals a omega squared. Now, when the dust settles, right, what we find here is that the omegas cancel from the argument of sine, and we simply wind up with pi over 2, right? And that's great because pi over 2 is 1, or sine of pi over 2 is 1, right? Pi over 2 itself is not 1, but sine of pi over 2 is 1. And we then find that g equals a omega squared, otherwise known as a equals g over omega squared. And this is the answer. Okay, so let's see here. So if it were cosine, then n of t equals 0 when at 0t or 4t. Oh, geez, it's too late to be thinking about that stuff. But we can plot it, right? We could just see, like cosine, right, is 0 at... Is it still 1/4 of the period? Because it's like 1.57 here, right? And the period is 2 pi. So I think it still happens at t over 4. Right? Somebody sanity check me here. Let me just try this. So 2 pi is here. This should be 3/4 of 2 pi. This should be 1/2 of 2 pi. This should be 1/4 of 2 pi. 1/4 of 2 pi is still pi over 2, right? So it still happens at t over 4. But look, the point is that you can always, like as I've been saying, right, you can always plot these functions really quickly just to get a handle on what they're doing, right? And that's one of the great things about this is that you have your calculators, you can just, really quickly plot sine or cosine. And no, it doesn't end up mattering, right, with whether you choose cosine or sine. But like I said, I would choose sine here because of this reason, that this is a very natural thing to enforce, that its position, its y position at time t equals 0 is 0. Right, so how do we get negative a omega squared sine of omega t to substitute for a y? Well, that is just from this, right? Remember why we said that y of t is a sine of omega t, and then we just took the second time derivative of this. And that's just math, right? That's just taking two derivatives. And I mean, I guess I should say it's just math because like I've messed this up countless times, but like, we could always just put this on our formula sheet that if, y of t is a sine of omega t, the second time derivative of it is negative a omega squared sine of omega t. Let's see here. Wait, why is it sine of t over 4? Okay, this is a good question. Because okay, you know what I want to do? I think maybe plot this with the values they give us. That might be a good thing to do. So I'm going to cheat here and use my answer, right? But I'm going to plot. My amplitude is 0.118, right? And sine of, and then omega, right? They give us the regular frequency. We need the angular frequency. So they give us f, we need omega, right? But omega is 2 pi f. So just 2 pi times 1.45, which is my frequency, all times t. So this was our y of t, right? I'm just plugging in the numerical values that I have from the assignment into this equation, right? Y of t equals sine omega t. Because remember, this is also 2 pi f, right? And so let's look at this, and let's look at it over, I don't know, let's say like t goes from 0 to 5 or something. Let's see. Maybe we'll do like 0 to pi. Because this is a wiggly boy. That's a little better. Okay. So look, remember, right? Y of t is on the vertical axis here. On the horizontal axis, we have time. And so the first thing we said is that at time t equals 0, the y position is 0, which is true, as evidenced by the graph, right? Now, this is t over 4, right? This peak. Now, this 0 is t over 2. This minimum, or trough, is 3t over 4. Or wait a minute, is it that? Yeah, it is. Okay, I'm confusing myself. So at this peak, I'll zoom in too, just in case. At this peak is big T over 2. No, big T over 4. Jesus Christ. Big T over 4 at the peak here, okay? This 0 is big T over 2. This trough is 3t over 4. And this 0 is now big T, right? And so that's why I said, let's look at time t equals big T over 4. Because I knew it would be, I I knew sine would be at a maximum there. Okay? And I would be shit out of luck probably if I couldn't plot this, right? So again, just graph it on your calculator if you want to try to see what's going on. All right. But this is a representation essentially of what's happening, right? This is the y position as a function of t. Yeah, I believe so. Okay, I believe it will always be big T over 4, but just do your due diligence and check on your calculator, okay? Because like I'm tired and my brain is not working great, and I don't want to lie to anybody, okay? But if it is sine omega t, then yes, it's definitely big T over 4 for the first maximum, okay? Cool. All right, is this clear? Like I said, I think that there's a lot going on here that's like good for everybody to be sure they understand. So, are there any further questions about this? And just to make sure it's not just t, it's big T over 4, right? Where big T is the period, not little t, because little t is just time. It's just arbitrary. And I would say like definitely this would be a good one to work through to make sure you understand that you can, you understand everything that's going on here and that you can replicate this result, right? So I would encourage everybody to do this. I will move on now. Are there any other questions about like homework problems or example problems or anything like that that people have? Let me see. I will see what Nero's. I haven't really looked at that in too much depth, honestly. But I really think that Nero's practice exam is much harder than the exam you're all about to take tomorrow, and I also think that it's not a great representation of what you'll be expected to do. So, looking at number 2 here, I'm very inclined not to do this, okay? Because this is not. I don't think this is going to help very much. So if you look at this and you're like, what the fuck is happening? Don't freak out, okay? Because this is not going to really ruin your chances tomorrow, okay? Let's see, a hinge one or something similar. Let me look at this like assignment that I gave you here. Does anybody have any questions about like this? I don't know that I actually really like these problems either. A hinge problem. Let's look at like, yeah, let's look at a hinge problem maybe. Let me see if I can just find one really quickly that we can keep general. I think that'd be good. I kind of like this one that I found before. I think it's from the OpenStax textbook, so let me see if I can just bring that up really quickly. Bear with me here while I try to find this. Okay, it's this. This is like this isn't a bad resource because it's free, and I think that for the most part, oh wait, it was about to take me right to where I wanted to be, which is here. So statics and torque. And let's look at these problems here. Okay, what the fuck is this? Really? Where is it? All right, bear with me. Because I would like to do a hinge problem. Just to make it clear to everybody what I'm talking about. Okay. This is like really. So I'm just looking at the question from Chegg, but this is fine, I think. So yeah, we can do this. Oh, it's been solved. I could just sign up for an account and show you guys instead of having to do it. Let me see if I can do something here. Save image. You know what? Let's not do that. Let's do this. Okay. Practice problem here. Yeah, okay, I like this. So we have that the sine waves, let's call it big W, is 205 newtons. And the guy wire makes an angle theta equals 25 degrees with the horizontal. This is a good one, I think, actually, because this will also give us some practice with like this angle and calculating torque and stuff too. What else do we have? We have that the beam has a weight also. The weight of the beam is, we'll call it little w, is going to be 170 newtons. So I can just, as I'm getting this set up, I guess, talk about. So how do you know when to use the parallel axis theorem? Basically, it's like when you have a simple object that we already know the moment of inertia for, when considering an axis passing through the center of mass, and we just want to figure out what the moment of inertia is through a different axis that is parallel to the center of mass axis, right? So it's basically always going to involve using one of those ready-made formulas that we were looking at earlier to just figure out what the moment of inertia is through some other axis, right? So again, the typical example is the rod, where you use the parallel axis theorem to go from the center of mass of the rod to one of its endpoints. But you could also do this for a sphere, you could do it for a disc, you could do it for a hoop, right? These are all possibilities. Okay, so this weight of the beam is blah, blah, blah. All right, I'll probably have to make a sketch here. So let me do this. And I just want to clear out this crap. Okay, so this is the situation. We need to think about like what the different forces are that are acting on this beam, okay? So bear with me, I'm gonna draw with my mouse. It's gonna be awful, but hopefully it gets the point across. So what we're gonna have, right, is first of all, most obviously, we're gonna have a tension force here in the wire, right? And this is gonna point along the direction of the rope. It's supposed to be a straight line. Okay, there's that. Now we're going to do this thing about the hinges because like the beam is definitely in contact with the hinge, so we have to, you know, guess about what the force might look like there. So I'm going to do exactly what I said, and I'm just going to say, okay, there's an x component to the hinge force, hx. There's a y component to the hinge force, hy. Okay, it's supposed to be a y. There will be, right, this is important too, the beam here has mass, right? Because we're told it's weight. And so there will be a gravitational force here on the beam pointing straight down, and I'm going to call that little w. There will also be a force on the sine, right? Which we'll call big W. Now, we can probably convince ourselves that like the force, the gravitational force exerted on the sine is the same magnitude and direction actually as the tension force that this cable exerts on the end of the beam, right? Are we all good with that? Is that okay? So what I would be inclined to do is just draw this force up here. Yeah, so they're being, I don't know, I don't like it when they do this either, but they're just being annoying and giving us the weight instead of the gravitational force. But in the issue with that is that sometimes we don't get cancellations that we otherwise would, but it's fine, right? Because if we really wanted to, we could just quickly solve for the mass of the sine and the beam by dividing by g, right? But we don't really need to do that. Okay, so this is just a very typical static equilibrium problem. So what we do is we sum our forces in the x direction. And somebody was asking about this earlier, and this is where we'll see kind of what the point is of actually writing out the torque expression, even though we know that the net torque is 0, right? So what we have here is we have the hinge force, the x component of the hinge force, and that points to the right. We just guessed right that it points to the right, but we're actually correct because we'll see right that we have to subtract from that yeah, they made it easier. Yeah, hey Lucas, what's up? That we have to subtract from that the x component of the tension force. Okay, so that is going to be given by t cosine theta. And again, static equilibrium, right? We set this all equal to 0. Cool. So we do the y equation now, right? This is a bit busier because we have the y component of the hinge force, the y component of the tension force, and we also have both the weights pointing downward, right? So we have the little weight and the big weight. And this is all equal to 0. Very cool. So far, this is probably not weird or unusual because we've been doing this, you know, pretty extensively, right? Just Newton's second law. But now this is where it's a bit different. So the first thing to do, right, with a torque problem, a static equilibrium problem like this, is to decide where our origin is, or rather our axis of rotation, right? And so I would put that here at the hinge, and we'll just call it P. So what we do is we say the torque about the point P, or about, more precisely, the axis passing through the point P, is just given by the sum, I should put a net, the vector sum of all the individual torques that we have here. So let's start with, I need to make some other symbolic declarations here. Let's just say that big L is 1.70 meters. And we'll say that little l is 1.35 meters. Okay, so we're good now. Okay, so the beam is presumed to be uniform, which means that we can imagine that all of its mass is concentrated at its geometric center, right? And that's why I drew the weight force where I drew it. And so this is going to be, the weight force will give us a torque that will tend to make this thing rotate clockwise. So the sign should be negative, right? So what I would do is I would write negative W, that's little w, my bad, times L over 2, right? Because remember, torque looks like RF. So my R is L over 2, and my F is W. And one more time, right, we can all probably see that if, you know, if it were just this force alone acting on the beam, it would definitely start to rotate clockwise, right? Which is why I put the negative sign in front of this. We'll knock out the sign also, the hanging sign, and that's going to be just big W, L, right? because it is acting at a distance of 1.7 meters from the hinge. And will also tend to make this thing rotate clockwise. Okay? So we just have to account for the tension force now, because like if these were the only two forces acting on this thing, we would see that it would definitely have an angular acceleration, right? A non-zero angular acceleration. So we have to be careful here, because like what we really want to think about is the component of the tension force that's perpendicular to the beam. So we could call this T perpendicular if we wanted to, right? And so then I'll draw this again over here just to be sure we get the trig right. But like this would be the X component of the tension force. This would be the Y component of the tension force. So this again is T perpendicular. Okay? So we see, right, just to be deliberate about this, that T perpendicular, yep. Let me do it like this. Sine theta equals opposite over hypotenuse, right? So it's T perpendicular over T. And so this tells us that the component of the tension force that we care about is given by T sine theta. Okay? And we have to remember to multiply this expression by little l in our net torque equation. Yeah, I'm doing that right now. It's a good question. It should be in there, and I'm just making sure I get the geometry or the trig correct, right? But it does appear, and it's this. And then this is all equal to 0, right? So these are our three equations. What do we want to solve for again? We want to solve for, I know we want to solve for tension, right? That's the one thing. We want to solve for the tension. And that we can do, right? Let me just start here. So solving for tension, we focus on the torque equation. Now, I forget who asked about this earlier, but this is an example, again, where like the net torque is 0, but there's a term in there that we care about. So it's not useless to write out the net torque equation, right? And solving for T, we can just say, I'll do this like step by step, but definitely let me know if I make any algebra mistakes. We can write something like L T sine theta, and then we just add these W terms to the other side. So we get equals L W over 2 plus L big W, right? We're just doing the algebra now. And I mean, the only thing left to do here is really just divide both sides by L sine theta, right? So what we find is that T equals LW over 2 plus L big W. Now I'll make this look different. That, and then what do we say? We divide by 2L sine theta, right? This is our tension force. Let me just check the algebra here. I think it looks good. If you see a mistake, let me know, but I think this is it. This is our tension, right? You plug the shit into your calculator, you get a number, blah, blah, blah. Who cares, right? But that's it. So wouldn't you have to extend the R for the tension? Why wouldn't it be T sine 180 minus... Oh yeah, good question. There's no 2 in the denominator. Thank you. That's good. So that should be okay. Thank you for that. I have to extend the R for tension. Because remember, right, that one of our definitions or results for the torque was wow. Where the hell was it? Here, right? Is that just because this is defined by a cross product that we could write the magnitude of a torque in these equivalent ways, right? RF sine theta, or R times the perpendicular component of F, or the perpendicular component of R times F. So I did this, right? I did this. And that's all there is to this. I might have, yeah, geez, it's 10. I might have time to like start an angular momentum problem at least. We could do that next, but that'd probably be the last thing. So let me just like knock this one out really quickly, and then we can look at an angular momentum problem. And yo, if you want to like find an example problem you want me to do, and then just like, I don't know, like just search for one online maybe and just post the link in chat, that'd probably be the most efficient thing. Preferably one, right, where like that shows the concepts we were talking about, which is like the different types of, you know, orbital and spin angular momentum, and, you know, applying conservation of angular momentum for that stuff. But okay, so this is our tension. Hopefully everybody's good with this. The other thing that we had to solve for, I guess, was the hinge forces. And yeah, so we could do this like in one line now, right? Because with the tension in hand, we refer to our x equation and see, right, that the x component of the hinge force is just T cosine theta, right? Because we did this. We already wrote out our net force equations, like this, right? And so that's it, because we already have T. So all we do is we just like multiply this by cosine theta and we have it. So I'll just do that. Just this times cosine theta. Okay, cool. So then that's the x component. I guess that's all we're asked to do here actually, but let me see about the y. Like we could even solve for the y if we wanted to as well, right? Because we would just apply this equation. And we now know the tension, the weights, both the weights are given. So it would just be a matter of plugging in the tension into this equation and then isolating the h sub y. Is everybody good with that? The last thing I think I want to say is just like notice that we guessed about the x component of the hinge force here, but it was correct, right? And it had to be correct because the only other force acting in the positive or negative x direction was the x component of the tension force, and that was pointing to the left, right? So to have static equilibrium, the hinge force must, the x component of the hinge force must have pointed to the right. Okay. Now, if you were to go through and do the math and plug in T here and like evaluate the number and all that, there's a chance, right? There's a chance you could get a negative value here, but that's okay because all it means is that we assume the wrong direction, and it still has the same magnitude. It just points down, and it's entirely possible, but I don't feel like it's necessary to go through and do. So I'm going to leave this at this. Let me see this problem that was posted here. Yeah, this is a great one. Let's look at this. So this is an angular momentum problem. Can I save this? Oh, I don't want to do that. Let's do this thing. Okay, so this is the, wow. Yeah, let's knock this out and then we can call it quits for the night. Okay, cool. Okay, so a large wooden wheel of radius big R and moment of inertia IW about its axis of symmetry is mounted on an axle so as to rotate freely. A bullet of mass m and speed v is shot and moves in a straight line. Neglect gravity, tangential to the wheel, and strikes its edge, lodging in it at the rim. If the wheel was originally at rest, what would its angular speed be after the collision between the bullet and the wheel? Okay, so let's go through this carefully and deliberately, right? So, let's say right before the bullet is lodged in the wheel, there's only orbital angular momentum. Okay, I'm like thinking way too hard about how to write the words. It's not really important. There's only orbital angular momentum, let's just say because of the bullet, or because the bullet is translating. And the wheel is not yet spinning, okay? So we could write this. We could write, just to be, again, very careful here, J naught equals L naught plus S naught. But this, of course, is 0, right? So we'll just strike it out because nothing is spinning about its own axis. Now we fill this in. Let me do this. We fill this in, and we already kind of know that this is going to have the form RMV sine theta. Now let's just check, right, to make sure that we get the sign correct here. Even though it doesn't really matter in this case because the orbital angular momentum and the resulting spin angular momentum will have the same direction, right? But let's just check. So we take our origin to be the center of the wheel, right? And we then, that tells us what our position vector is, right? So our position vector takes us from here to the edge of the wheel. So take your right hand, point your fingers in the direction pointing from the center of the wheel to where the bullet strikes. Then you curl your fingers in the direction of the bullet's velocity. And so it would actually be, I guess it would technically be negative. Let's just do that, right? Assuming that x points to the right, positive x points to the right, and positive y points up. It would technically be negative, but we'll see that it doesn't end up mattering. And we're just going to make this correct. I'm not going to use MB and VB because there's no point in writing subscripts. And furthermore, the velocity vector of the bullet, right, is going to make a right angle with the r vector. So this should just be sine of pi over 2, which is of course 1, right? So this equals negative r mv. So what would the spin angular momentum be if the wheel was not? Well, we would have to account for that, right? If it was spinning one way or the other, we would have to write, essentially we'd have to write plus or minus I omega here, right? Where I is the moment of inertia probably of a disk, or actually we're given it here, it's just IW. And omega would be its angular speed, right? So if the wheel were spinning to start with, we would put plus or minus I omega over here, and the plus, or the choice between plus or minus would be dictated by which direction the wheel was spinning, right? Is that clear? It's a good question. But the point is that it would be non-zero, right? The spin angular momentum would be non-zero. Okay, cool. So what you should do, right, for those of you following at home, you should draw these vectors and make sure that what I'm saying here makes sense, okay? Confirm all this stuff because it will help you understand what's happening. It's just, like I said, it's just difficult for me to draw everything because I have to do it in Paint and it's, you know, looks shitty. But this should be good. Okay, cool. So after the collision, you know, we don't need to know really anything about physics to know that the wheel is going to start spinning, right? Like you could have told me that before you set foot in Hattridge's class this semester, right? So I'm just going to say after the collision, the wheel will clearly begin to spin. And now we have to consider the total angular momentum after the bullet is fully lodged in the wheel. Wheel has an H. So I would write J right now. This is the final total angular momentum, and it's just going to be L plus S. Now there's no orbital angular momentum, right? So we just get rid of this because this thing is just one object now, right? It's a combined object that we can just think of as one object that's spinning, and it's actually spinning about its center of mass axis, or an axis passing through its center of mass. Can we get points if we don't really know the equations or what to set up, but we write out some sentences like you're doing? Honestly, I like people will write sentences out. It drives me crazy because they'll write sentences out. They'll be like, "This is what we should do," and they'll be exactly correct. And it's just like, why didn't you just do it? You know. But I don't know. I guess we have to see. Okay, so this is going to look like negative I, and I'm going to write I total, and you'll see why I'm doing this in a second, omega. Right, now, again, it would be a good idea to do the right-hand rule here and just make sure that this negative sign out in front of our expression makes sense. And indeed it does, because we curl our fingers in the direction of omega, right? Or rather in the direction of the spin, and our thumb points into the screen, which would be our negative z direction if positive x points to the right and positive y points up. Okay, so I hinted at this earlier, but we see that these negative signs don't end up mattering. But you should still be very careful with them because sometimes they can. Like for instance, if the disk was spinning initially, right? Okay, so at this point, we just have to fill this in. We just have to note that we could probably treat the bullet as a point mass, right? And so our moment of inertia is then, and this is what I was saying before, it's just like the moment of inertia of a wheel plus the contribution from the bullet, which would be this. Just the mass of the bullet times its perpendicular distance from the axis of rotation squared, right? And then omega is just omega. Okay, so finally we equate the two. We equate, let me just say we equate J naught with J. And we find negative R mv equals negative I w plus m r squared omega, right? And we wanted to solve for the angular speed, right? We don't even need the angular, we don't even need the direction. We can just make sure that we write it as positive. And it's just a matter of dividing both sides by this crap, right? So we get that it's going to be RMV over IW plus MR squared. And yes, the little m is just the mass of the bullet because look, we were given the moment of inertia of the disk, and remember that the moment of inertia takes into account the mass, right? So it's totally fine here that we don't know the mass of the disk because all we really care about is the moment of inertia. So is I omega 1/2 mr squared. Not sure where you're getting that. because oh, I see. My bad. Yeah. Okay, that actually is a very sensible thing to ask. I apologize. IW, well, it could be, right? And if we knew the mass of the disk, then we could also write that. Yeah, that's a good question. It would just be 1/2 mr squared because that is the moment of inertia of a disk, right? So yeah, but they're making it even easier on us because they're just telling us what the moment of inertia is. But yeah, we could, let's say we knew the mass of the disk and it was like big M, we could just substitute in here 1/2 big M r squared, right? And that's fine. But we'll leave it in terms of what they give us. It's just this. I read the W as an omega. That's what messed me up. Okay, so this is a pretty typical kind of problem. And what I would very strongly suggest you do is just think about what happens here when, or if rather, the disk initially has some angular velocity, okay? And just kind of see how that would change things, right? And I mean, like we sort of know from our intuition about the world, right, that if like the disk were originally spinning, say, counterclockwise before the bullet struck it, it wouldn't be spinning as fast finally as it is in this case, right, where we're thinking about it not having any angular velocity initially, right? And then, you know, the other thing would be if it were initially spinning, if the disk were initially spinning clockwise and we went through and we did this exact same process, except obviously accounting for the spin angular momentum it would have in that case, then the final angular speed of the disk bullet system would be larger than what we found. Is this making sense? Like what I'm saying here, is this good for everybody? Okay, cool. So yeah, those would be great things to think about and just work through. Generally, you could make up numbers if that helps, right? You know, it's probably not too difficult to come up with some reasonable numbers here, and just try your hand at the different cases because the most general situation would be that the disk is initially spinning some way, right? Whether it's clockwise or counterclockwise, and the bullet strikes it in the exact same manner, and then you just kind of want to think about what happens. And doing that, you know, you could actually look at your result and then just take the limit where the initial angular speed of the disk is 0 and confirm that you get what we just got, right? Because that's a great thing to make sure you obtain, right? Okay, cool. I think I'm going to end here. If you have any questions, of course, between now and the exam, hit me up. I'll do my best to get back to you. I'll probably try to get like to alumni maybe like an hour before the exam tomorrow. So if people have last minute questions, I'll be there. I think I kind of want to raid somebody. So I don't know. You can leave after I do that, but like it's fun, right? I mean, raiding people. But yeah, hopefully. Oh, and if you haven't followed, by the way, please do that. I appreciate that. Obviously, it doesn't cost you anything, and it helps me out. There's this Canadian streamer. He streams Age of Empires 2, who I like. I'll probably just send you guys over to him. He's a good dude. I actually mod for his channel. See if this works. So I'm just gonna like send you all over to another channel. Yeah, it's just like a dorky Twitch thing. Yeah, no, no, God, no, not Raid Shadow Legends.